Hi everyone, I am Saniya Kule. This is cute little Yangshi. Woo! And in this video, I want to do something important related to decision curve analysis. I want to help you better understand how we derive the probability threshold interpretation. So what does the probability threshold mean in decision curve analysis? Because we see it in the formula. So how did I derive the fact that probability threshold over 1 minus probability threshold is equal to the ratio of false positives over false negatives? How did we derive this? Because in the original paper by Andrew Vickers et al. In 2006, which was introducing this novel idea of decision curve analysis, there's a statement here, and there's more, but this is what I wanted to show for this beginning. The statement here says that the threshold probability at which a patient will opt for treatment is informative of how a patient weighs the relative harms of false positive and false negative results. And then I talk about in other videos, please do see those, please subscribe and see those as well, about how a probability of threshold of 25% is interpreted, how many different probability thresholds are interpreted. And I often go back and talk about this over here, this formula here. Probability threshold over 1 minus PT is false positive over false negative, as I was mentioning, and how this is part of the decision curve analysis formula for calculating clinical net benefit of a predictive model or approach. And we go into that, more in other videos too. But why is this the case? Why can we say that? And what does this mean? Why does it say that this probability threshold here kind of tells us about relative harms of false positive and false negative results? Why is this the case? So that's what we're going to talk about in this video. It's going to be kind of mathematical a little bit, some derivations, but this will be a very important foundation for us to move forward with. So again, I'm Saniya Kule. This is cute little Yangshi, and let's get started. And if you haven't, please do reach out with any questions, and please let me know any way I can help as well. And please do subscribe. But this is what we're going to talk about here. So for reference, just please note that this is the original paper by Andrew J. Vickers and Elena B. Elkin. Decision curve analysis, a novel method for evaluating prediction models. This is kind of what this will be based off of, and I'll be kind of talking to you more about equation 1 and beyond of this paper. So if you think of it in this way, this is a decision tree. And if we look at a decision tree for the treatment of a disease, for instance, you can see that if you have a disease or you don't have a disease, so let's say that the probability that you have a disease is given by P. So you can go for treatment or you can choose not to go for treatment. And you have different values from these outcomes. So if you go for treatment when you have the disease, then that is a true positive. So in this case, the positive class is having the disease. So disease is the positive class, and the negative class is not having the disease. So it's a negative. So if we're going for treatment, we're sort of predicting that we have the disease. So we're kind of predicting that we're positive. But if we choose not to go for treatment, then we are predicting like sort of negative. So a true positive is we are predicting that we should go for treatment because we have the disease, and that is a true positive. Whereas a false positive is predicting that we should go for treatment, but in reality, we don't have the disease. So what this part here represents is the reality, like the actual truth. But over here, what we observe is that this is the treatment or not treatment. This is sort of like what prediction or what kind of action we take given what we are predicting will happen. So this is the action that we take here. So what you observe here is that we are predicting treatment. So we are predicting that you would actually have the disease and that you would need to get treated for it. So if we go for treatment, the doctor or we decide to go for treatment, then doctor, nurse, we decide to go for that. That means that we're predicting that we're positive. So if we actually have the disease, then it's a true positive, and the value of a true positive is A. But if we actually do not have the disease, then that's a false positive because we are going for treatment. We're predicting that we will have the disease, but we actually don't have it. So it was a false positive, a false alarm. But if instead we don't go for treatment, then what we're predicting is that we're negative, we don't have the disease. So because we decided we're not going for treatment. But if we actually have the disease, this is the actual truth, then the outcome is that it's a false negative because we falsely predicted we would not have the disease. That's why we didn't go for treatment. So this is a false negative. If we don't go for treatment and in reality we don't have the disease, then that is a true negative. So these are the set of outcomes. So here A is the value of a true positive, B is the value of a false positive, so this is an error. C is the value from a false negative, and D is the value from a true negative. So these are the actions given the actual truth. And this is a decision tree because we are taking an action at this point here. We're deciding, are we going for treatment or are we not? And that's sort of based on what underlying assumptions that we have at that moment and what our risk tolerance is for false positives versus false negatives. So we kind of talk about this in other videos, so I'm just going to kind of go over this a little bit quickly. So please do subscribe and please do watch my other videos and reach out with any and all questions that you have. That's what Yangshi is requesting. In these cases, we have two outcomes to predict, and y equals 0 typically means that you don't have the disease or condition, and y equals 1 means that you have the disease or the condition. And you have a predictive model in our situations that you could use. And the predictive model takes a bunch of data like on the patient, for instance, and it can be many kinds of things, logistic regression, neural networks, all sorts of models are possible. And that's a whole other beast in and of itself. We collect data on the patient and we predict some output. And the output is usually taking in the patient data. What is the predicted probability that the patient has this disease? No disease, a healthy, happy SpongeBob, having the disease, the kind of unhealthy SpongeBob. So we get a predicted probability of having the disease. And we kind of put that through a classifier in a way, where essentially we're predicting that the individual does not have the disease if the patient's predicted probability of having the disease is less than some probability threshold PT. Otherwise, we predict that the individual has a disease, that y equals 1, if the patient's predicted probability of having the disease is greater than or equal to this threshold. And typically, the thresholds have been 50% in some cases, but in medical decision making, we kind of stay away from 50% necessarily, and we can look at other thresholds because sometimes the errors may not always be the same. And I talk about this in other videos too. So an overview of the machine learning models and how we can make clinical decision making based on probability thresholds. So again, we have patient data. We give the patient data to a machine learning model which predicts the probability that an individual like Pucci has a disease. And the doctor then decides based on the probability threshold where if the patient's predicted probability of having the disease is greater than or equal to the threshold, the doctor will predict positive that Pucci has the disease, and if instead the predicted probability is below the threshold, the doctor will instead predict negative that Pucci does not have the disease and is healthy. So this is the standard pipeline. And the unknown truth is actually at the time of the prediction is whether or not Pucci actually has the disease. And in this case, we don't know that Pucci actually had the disease here. So if the doctor correctly predicts that Pucci is positive, then it's a true positive. But if instead the doctor had wrongly predicted that Pucci is negative, because predicted probability Pucci has was less than the threshold, then this was a false negative because the doctor predicted that a positive patient, Pucci, who has the disease, was instead negative and healthy. So Pucci, who needed the treatment for the disease, missed out on the treatment on time. He's sad. It's okay. It's okay, little guy. The same pipeline, but whereas if Pucci is negative and Pucci is actually, healthy and does not have the disease, woo! Celebrate, 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 woo! All right, it's all right. Then the same predictions by the doctor could be interpreted in different ways. So if the doctor predicts that Pucci is positive and has a disease, and this would be a false positive because Pucci actually is healthy and does not have the disease. So the same prediction would be a false positive. Whereas if the doctor had predicted, predictive probability less than the threshold, so predict negative that you don't have the disease, Pucci, then this is a true negative prediction because the doctor correctly predicted that a patient who's healthy does not have the disease. So that's good. So then we talk some more about the two key spots in helping determine if predicted outcome is correct or incorrect. The first spot, so Yankee saying the first key spot is the strength of the machine learning model. Does it output correctly, given a set of data, right? Like how accurate is it in terms of making predictions? It's studying really hard to be able to take in patient data and to correctly predict as much as possible in the real world whether or not, like, the patient has the disease or not, but it's trying to output predictive probabilities. And we hope that the higher the predicted probability is, if it's that it should be really high, really close to 1 for people who have the disease, because 1 means you have the disease. So it should all, in an ideal world, the predicted probability of you having the disease would be 100% if you have the disease, and it would be 0% if you did not have the disease. That the predicted probability of you having the disease, given that you don't have the disease, should be 0. In an ideal, in an ideal world, that's what those probabilities should be. But often in the real, in predictive models, that may not be the case, and they would definitely give some number between 0 and 1. So we want it to be closer to 1 for people who have the disease, these predictive probabilities, and closer to 0 for people who don't have the disease. So the strength of the machine learning model will also impact the results that we get, because based on the predicted probabilities, we then apply a probability threshold, PT, for our clinical decision making, where like for patient Pucci, we predict Pucci is negative, does not have the disease, if Pucci's predicted probability of having the disease is less than this threshold probability. And instead, Pucci, we predict Pucci is positive and has the disease if Pucci's predicted probability of having it is greater than or equal to the threshold. So this is sort of like the decision-making part. So the first part, these predicted probabilities, are the responsibility of the machine learning model to try to be as close as possible, have lower predicted probabilities of having the disease for people who don't have it, and higher predicted probabilities for people who do have it. And the next is that threshold that we put this through. What does this threshold mean? And this is what we'll be focusing on in this video, kind of what this threshold that we are putting these predicted probabilities through, what this kind of says about it. And I want to derive the formulas that I typically talk about, how the probability threshold over 1 minus the probability threshold kind of talks to us about the false positive harms over the false negative harms. And I want to just show why that's the case here. And this is something that's also used a lot in economics and in risk calculations. This is a decision tree. So anytime we need to do decision making. So at some points, when you're deciding on the action, so again, guys, this is the action step here. This is when you are deciding, and this is a nice SpongeBob reference with Patrick and Sandy, sort of deciding on the action. And what this part here is the actual truth that we wish we knew, but we sometimes have to act without knowing it, with the hope that our model or what we know is correct. We're going off of an assumption, and the probability of the disease is P. But we're taking an action. Either we go for treatment or we don't go for treatment. So this is us over here. We're not too sure what is the outcome that we want to go for. So we're not really sure. We're really confused. Like, what should we go for? So a threshold probability is something where the key idea is that you're going to sort of look at the outcomes from going for treatment and you're going to look at the outcomes from not going for treatment. So if you go for treatment, the outcome could be that you have the disease, so it was a true positive, and you get the value of it. But there's also the chance that you don't have the disease, so you're getting the con of the false positive. So it's sort of like weighing it. So that's the result that you would get if you go for treatment. On the other hand, if you don't go for treatment, you also have the harm of a false negative. Like, what if you actually have the disease? Like, that's a risk you're going to take. You're not going for treatment. You could land up with the disease. But on the other hand, you might skip out on the treatment and you might not actually have the disease. So you have a true negative. So if you go with this outcome, with this action, and these are your outcomes, and these are the results of the action that you've taken. So if you decide for no treatment, you're getting essentially a false negative and a true negative. You're getting whatever the value is of that decision. On the other hand, if you go for treatment, and you don't have the disease, you're getting the cons, the weaknesses of the false positive. But if you actually have the disease, you're getting the benefits of the true positive. So you will, of course, weigh these in your mind, and you're going to think about it. Like, maybe it's really horrible, what you would miss out on if you actually don't go for treatment, and the false negatives are just too much for you, versus the false positive. You really don't want to risk not going for hospitalization if you actually have severe COVID. Or let's say for cancer, you don't want to not get treatment for cancer, and to risk that and find out that it could have been prevented, your life could have been saved, or even better, if you had acted before your cancer went to an advanced stage. So you might want to really avoid the false negative, given this probability of having a disease. But what happens is, at the threshold, there's something that happens. At the threshold, so you're weighing this outcome of going for treatment, this action, with not going for treatment. And at the threshold probability, the value equalizes in a way. So the value in a way of going for a true positive is A multiplied by this threshold probability. So what happens is, when you go across a decision tree with an action, and each action has a predicted probability, so these have to sum to 1. That's always the case. In a decision tree, these outcomes here, they sum up to 1. So this sums to 1. And same with this sums up to 1. What you then see is the value of an outcome. You multiply along the branches. So you see that this is the threshold probability. You multiply it by the value of this outcome, and you get a weighted value, which is A times PT. So for no disease, what you will then get is you're going to multiply it out. So what that value is going to be B multiplied by 1 minus PT. That's the value of this false positive. So similarly, for not going for treatment, given that the same probability of disease is here, PT here, you're going to multiply it, this PT times this C, multiplied by C. And then similarly, for no disease, what the outcome you're going to get, the value, this is going to be D multiplied by 1 minus PT. You're going to multiply these out, and you're going to see what is the value where this is the benefit of going for treatment, is A times PT plus B times 1 minus PT. This is the value that we get of going for treatment, the value of a true positive plus the false positive. That's what this value is over here, is this value here. That's the value of treatment, and the value of no treatment is given here. It's given here by PT times C plus 1 minus PT times D. That's the value of not going for treatment. And at the threshold, you're sort of on the cusp.
You're sort of on the threshold of deciding, do I send my patient for treatment or not? Or if I'm the patient, do I go for this treatment or do I not go? And it's right at that moment where the two actions, going for treatment or not going for treatment, the benefits, the pros and the cons. So the true positive, the benefit, plus the con of the false positive is the same as not going for treatment, the false negative plus the true negative. So at the threshold, the benefits are equal to each other. The expected benefit of going for treatment, that expected benefit is the same as the expected benefit of not getting the treatment. So you're sort of like not sure what do you do. And the way I think about it is that if you, hopefully not, but let's say you were predicted as having cancer, and you find out from the model or the doctor tells you that you have a 20% chance of cancer, would you go for treatment or not? But what if it was 21% chance for cancer? What if it's 22? What if it's 23, 24, 25? Okay, 25, I'm going for treatment. Then my threshold is 25%. That if I have a predicted probability of disease of 25%, then that means inherently that I don't want to take the 25% chance that I am not going for treatment and I could have cancer. So that inherently informs you about my risk preferences for false positives versus false negatives. So this is the equation here where you sort of equalize them together. And you then are going to see how this all works together beautifully. So at the threshold probability, you can figure out indirectly without any external information about how many life years it cost or how much this chemotherapy really cost or the stress or the paranoia or the money, the hospitalizations or maybe cancer advancing to a late stage. There's so much data and information and subjectivity involved that it's really difficult, but somehow just knowing what is the threshold. Maybe for me, it's 25%. If I have a 25% chance of cancer, I'm going for treatment. For somebody else, that could be like 35% chance of cancer, or maybe 85% chance of cancer. It really, really depends, and it's really subjective. But from this threshold probability, what you can learn is maybe how does a patient or how does a clinician, how do they weigh the relative harms of false positive and false negative results? So from that decision tree we looked at earlier, we can set them equal to each other. And then we can just solve this out, guys. So we can just factor out this PT here, A minus C, and then factor out similarly this 1 minus PT, and then D minus B come out here. And then we just divide both sides by PT, and then we get this result here, which is really awesome. So you'll notice that this numerator here is A minus C. So A is a true positive and C is a value from a false negative. So it's sort of telling us, like, what is the result, the consequence of not getting treatment when you should have been receiving treatment? So what is the harm from a false negative result compared with a true positive result? The harm from a false negative result compared with a true positive result. What is this difference here? That's what it's looking at. Similarly, if we look at the denominator here, we see it's D minus B, which is the same thing as a true negative minus the false positive. So what that is saying is that what is the result or the consequence of receiving treatment when you should not have been receiving treatment? So what is the harm from a false positive result, which is what, like, receiving treatment when you shouldn't have been, compared with a true negative result? So that's what we find about the threshold probability. So that's what we can capture here, is how do you weigh the false positive versus the false negative results? So if it's at 50, if my threshold probability is at 50%, which it typically is in a lot of other applications, but in like healthcare especially, I feel like that threshold is not so equal because sometimes like saying somebody has cancer when they don't, for instance, and then giving them chemotherapy and other treatments may not be in some people's minds, and it's very subjective, and I respect that. In some people's minds, it may not be as bad as saying that somebody doesn't have cancer and then their cancer advances to a very late stage and it's too late to save them. So sometimes, a lot of the times, I feel like false negatives are worse than false positives. But if we say that the threshold probability is 50%, that means that false negatives is the same as false positives in terms of the error. But if it is greater than 50%, false negative is less than a false positive. And if it is less than 50%, that means like if I'm really going for a cancer treatment, if my probability is more than like maybe 80%, that means that I really don't want to make a false positive. I want to be super sure I'm going for cancer treatment. But what we typically observe is that many people might go for cancer treatment, even if that predicted probability is like 40%, for instance. So if they have a 40% chance of cancer and a 60% chance of not having cancer, people will focus on, I have cancer 40%, I'm going for treatment. So they value a false negative usually more than a false positive. So if it, in a way, if this threshold of PT is less than 50%, what we can learn from this is that the false negative is more important than the false positive. So that's what we can observe based on these thresholds. And usually in many applications, it's like 50%, so you're sort of indifferent. But I feel like in healthcare decision making, this threshold is very, very subjective.
Sometimes in life, we don't really know the value of a good thing till it's lost. I appreciate you every day, Yankee. He's the cutest cat in the whole world. So there are many quotes on this, by Theodore Seuss Geisel. Sometimes you will never know the value of a moment until it becomes a memory. So we often don't realize how good things are in our lives, touch wood, till something, God forbid, happens, or something that reminds us about the things in life that we should cherish and appreciate. So that's the kind of idea I want to, not to preach. I mean, I think it's important to appreciate all that we have, be super thankful for everything as well. I'm super thankful for you every day. He's a very cute guy. But the idea here is that, you know, the A, B, C, and D, they give the value associated with each outcome. A with a true positive, B with a false positive, C with a false negative, and D with a true negative. And the way that they give those values of these outcomes could be in terms like quality adjusted life years. From each result, if we adjust for the quality and everything else, like the life years you've saved, like some measurement of the consequences or benefits of certain results. But in reality, when we're going in, we kind of expect, usually, we know there's uncertainty, but we really hope, that predictions will be correct. Sometimes we might take for granted, how advanced life is, how predictions should be pretty reliable, like, true, we expect kind of like true positives or true negatives, right? But there's always scope for error, like false positives and false negatives can and do occur. That's why we talked about why it's important to have good predictive models and also a reasonable probability threshold as well, that based on your subjective beliefs as well. But to appreciate a true positive, correctly identifying that someone has a disease or condition when they actually have it, if we want to understand and appreciate this correct prediction, how we can do that is to compare it with a benchmark. Compare it with what would have happened if instead we had a false negative, like C. What if instead of correctly identifying your positive, we incorrectly predicted you were negative? That's like the worst case outcome, right? That's how we can appreciate the value of a true positive. It's in terms of the benchmark of a false negative. So we can compare A with C here. That's how we can compare A with C. And similarly, to appreciate the true negative, why is it important that we correctly predict you do not have the disease or condition when you don't have it? Why is that helpful? Or what is the value of this correct prediction? Well, we can think of the other side of the coin, the other side where, let's say, if we had to think about things and have a moment of appreciation, we would say that, okay, I'm thankful that it correctly predicted I did not have the disease when I'm healthy. Because what would have happened if I was, instead of false positive, incorrectly predicted as being positive when I actually don't have the disease and I went through unnecessary treatment? What would have been that impact? That's what we have to consider when we're looking at a true negative. What's the value of that? And of course, there are false positive and false negative, and we can weigh these on their own terms. But for a true negative, we weigh it against the benchmark of a false positive to really appreciate why this is really helpful. Like, what is the impact of this outcome? The impact is that we are spared a false positive. The impact of a true positive is that we're spared the consequences of a false negative. Speaking about comparisons, I actually found an analogy when people often talk about, just think of the glass being half full or half empty. They say, oh, don't think of it as the glass being, half empty. See it like as being half full, for instance. So that's kind of an analogy, two people can see things the same way, you can compare the results and see either that, hey, it's a true positive, but then you could see, oh, it could have been a false negative, for instance, and that's why the true positive is even better. Or it's a true negative. That's better because instead it could have been a false positive. So that's the idea. And I just found some inspirational things where people are asking, what is the glass? Half empty, half full, or 50% filled with liquid? And then again, this is like the full and empty idea. And then I found a very cheeky, very cute saying here I wanted to share with you guys that says that, technically this glass that is half full is filled with half water and half air. So technically the glass is always full. So that's a pretty optimistic viewpoint. And a biggest saying is that the greatest attitude is gratitude. So I really do like this idea. See the glass is always filled. Sometimes it could be completely filled with water or with air or with both. So it's always filled with something. And in that spirit, I also wanted to share some COVID masks that my friend and I made with a cute little bow tie. And the spirit is that, even in something very unpleasant and, like the pandemic, you can always, always, always make lemons. Oh, you can always, always, always make lemonade if life gives you lemons. So that's the idea. So we had designed these cute little tie-dye masks. So life is all about perspective. And we customized it with things that matter to us. So, even in the midst of having to wear masks and quarantine, you can always try to let your creative side out. So just a little spiel as well. But the key idea is that we do these comparisons in a way, and that's why we'll be focusing more on the false negatives and false positives in those equations. And I just wanted to motivate that to you in this way to sort of explain why, if we're looking at true positives, why do we compare true positives with false negatives? The mistake that could have happened if we didn't have a true positive. And why do we compare the true negatives with false positives? Why do we compare the true positives with false negatives? So as I was mentioning, I do cherish this cute little guy. He is so adorable. He's my heart, a little guy. I love him so much. But sometimes we don't really know the value of a good thing or something that we have in life, a person, place, thing, anything, until it's gone. So I needed to show kind of the idea of comparisons. So one of my favorite shows, SpongeBob, this is Squidward, and this is Squilliam Fancy Son, and Squidward usually compares himself a lot with Squilliam. So, if he's like an error, if he's like a mistake here, false positive, false negative, he can see what the effect is, of being rich, powerful, apparently like very popular and happy, for instance. That's what he sees about Squilliam's life. So he's always comparing himself and feeling small, smaller everything in life. So that's what he's doing. He's comparing himself. And Squilliam, who's like a true positive or a true negative, for instance, like can compare himself with Squidward. So as he's comparing himself with Squidward, so let's say that Squilliam Fancy Sun is a true positive, he can see that Squidward is a false negative, for instance, and what is the impact? So he can start to appreciate what all he has by seeing, in his opinion, maybe what it could have been by looking at Squidward. You know, they were peers growing up. He could compare that way. I'm not suggesting to compare, but I'm sort of saying that this is kind of something that happens as well. You know, that's something that we can directly try to do. You know, we can try to make this comparison overall. And the other idea is that we could see that if Squilliam is instead a true negative, he could compare himself with Squidward being a false positive. So the idea is that to understand the impact of a true positive, like why is it important for us to correctly predict that someone has a condition when they have it? We should see what would happen. Like, you know, why should we be appreciating this true positive? Well, understand what would have happened if we did not predict properly. Like, let's say that we instead predicted that somebody with the condition did not have it if we made a false negative. And why should we care about a true negative, you know, correctly predicting someone who does not have the condition, does not have it? Well, if we did not, for people who do not have the condition, if we instead say that they have the condition, then and make a false positive, it has a slew of effects. That's why for true positive A, we compare it with C, the false negatives. So we make this sort of comparison. We can compare these two with each other, and then we can also compare like these two with each other. We can make this sort of comparison. So appreciating a true positive by viewing what would happen with a false negative. And of course, with false negative, we have a slew of outcomes there. And from a false positive, kind of realizing why that is such a bad mistake. If we have a true negative, we can realize the power and why this is great by seeing what would have happened if we had a false positive. So basically comparing true negatives to false positives, and then comparing true positives with false negatives. And that way we get an appreciation. Like if we're Squilliam, we can see like in our situation, the worst case, and we can be appreciating for what we have. And ultimately, we hope that after comparing Squidward with Squilliam and doing this comparison, that in the end, Squilliam, you know, who here represents the true negatives or the true positives, those correct predictions, can come to see himself as a true positive, seeing the false negative side of things. And if he is a true negative, he can see the false positive side of things. So basically comparing the opposite perspective, and then getting some humility where he would say, oh my gosh, Squidward, I had no idea, you know, how difficult your life is. You know, I'm trying to imitate Squilliam, and having more empathy because he realizes when he has a true positive, how it could be a false negative instead. And how, you know, the tables could turn, how lucky he is, or when he's a true negative, how it could have instead been a false positive. So hopefully when he's figuring out and evaluating his life and his luck, you know, touch wood, he would be comparing it with Squidward's and then realizing, you know, that he is lucky. And in a way, that's the kind of thing we're doing when we're looking at a true positive. We're seeing the false negative error, and that kind of make us appreciate true positives even more. And when we look at true negative correct predictions, we look at false positive errors, and that can give us more gratitude and appreciation for true negative over a false positive. A way that I think about it is, what's the worst that could happen? You can imagine this guy's like me. See, he's running home. I don't know how I'm going to finish everything on time. And back home, cute little Yankee is fast asleep. He's fast asleep like this. He's just asleep like this, like a little guy. He's on the sofa. He's fast asleep. And it's like me saying, I should be like you and relax. What's the worst that could happen? And then the ship here is sinking, but he's always sleeping. So when again this A, B, C, and D, they give the value associated with each outcome, then, you know, if we have the disease or condition, if we actually are positive, then the worst case is a false negative C. So if he's saying, if the cat, you know, Yangxi's saying, okay, you have the disease and condition, you know, you're positive. What's the worst that could happen?
Well, the worst that could happen is a false negative, C, being predicted as negative, as not having the disease or condition when I actually have it. But in the best case, I will be a true positive. The predictive model and the clinicians, they will correctly predict that I have the condition if I have it. So here, it's not ideal to have the condition, but let's say you have the condition. The worst case is that it's not even detected properly. Well, the best case is that it's detected properly. And on the other hand, if you actually don't have the condition, if you don't have the disease or condition, you're negative, then the worst that could happen is that you're wrongly being predicted as positive, as having the disease or condition. So the worst case here is a false positive, is the machine, predictive model and clinicians are saying, oh, you have the disease or condition, you're going for unnecessary treatment. So that's the worst thing that could happen, Yankee. And the best case is a true negative where when you don't have the disease or condition, it's correctly predicting that you do not have it. But the worst case again, so if you don't have the disease or condition, if you're actually negative, the worst case is being a false positive B. But if you actually have it, if you're actually positive, then the worst case is being a false negative C. And to really hit it home a bit, so these are the predicted values and then these are the actual values. And this here is known as a confusion matrix, as Yankee showing. It's a confusion matrix. It's showing these four effects, these four outcomes, D, B, C, A. True positive A, false positive B, true negative D, false negative C. And we can see for the actual values here, how they are comparing. So this part here is you actually are not pregnant here. This one, you're not pregnant. This one, we are pregnant. On this part here, we are not pregnant. For guys, it's not possible for them to get pregnant. According to modern medicine and stuff too, it's not possible for a guy to be pregnant. And here, this lady here is, of course, pregnant. So actual values, not pregnant and pregnant. And true negative is saying that you're not pregnant, predicting you're not pregnant for this guy who is not pregnant. So he'll be saying, yes, yeah, of course, I'm not pregnant. Okay, well, that was obvious. There's no need for you to say that to me. That's what he's thinking here. But for him to appreciate why it's important that this doctor is predicting that he is not pregnant, that he is negative, it's important. So again, being positive means you're pregnant, you have the condition, and negative means you're not pregnant. This is what is standard and typically used. Positive is usually having the disease or condition. Negative usually means not having it. This is usually class 1, and then this negative is usually class 0. So he doesn't appreciate. He's like, yeah, I'm also like not. He can say, yeah, I'm also, like, let's say he doesn't have diabetes or something. Yeah, I'm also not that, or I'm also not blah, blah, blah. Like, he could say, yeah, I'm also not a lady. I'm also not this. So he's saying, you're saying the obvious, doctor. I don't really appreciate this insight, right? Like, I'm not pregnant. Of course, I'm not pregnant. So that's what he will think. He's a true negative in this situation. But for him to really appreciate why it's important that the doctor correctly predicted he does not have the condition, in this case, pregnancy, when he does not have it, this correct prediction, is because, like, let's say that the doctor instead tells him, hey, man, you're pregnant. This is actually kind of like a show like Jane the Virgin that I saw. It was such a good show. I really like it. And she was artificially inseminated, and she's a virgin, so she was really shocked to say that she was false positive, but she was inseminated by accident. But the reason why you should appreciate this true negative is, what if it was a false positive? Like, let's say the doctor came back and instead told you that, hey, you're pregnant. So when the doctor, he's saying, well, why did you have to tell this to me? Well, the doctor's saying, well, hey, at least you should be thankful. Like, let's say that I was a false positive and I could have told you that you are pregnant when you actually were not, right? So that's why he should be thankful in this situation. I know it's kind of like an obvious situation, but kind of try to imagine like a disease and she's predicting, oh, you don't have the disease. And he's like, oh, okay. And he doesn't really appreciate why, like, what's the meaning of this. The real appreciation comes if the doctor told him that there was this chance, or it could have been a false positive. And if you were a false positive,
then you could have gone through this unnecessary treatment. So you should be thankful that we correctly said you're negative. And in this situation, like, a true positive, for instance, like, the doctor is correctly predicting that the patient is pregnant when the patient is pregnant, then, having the condition when the patient has it, then the patient might say, oh, okay, yeah, okay, that's good that you detected that. They may or may not be really grateful. It really depends. But then in their mind, they would be thinking, and their gratitude would come from them realizing that there was a chance that maybe the doctor could have told them that they are not pregnant when they actually are. That's what a false negative is, saying, oh, you're not pregnant, but in reality, the patient actually is, but the doctor made a wrong prediction. And maybe because of that, the patient thinks, oh, I'm not pregnant, I can drink alcohol, or I can do all these other things that you should not be doing during pregnancy. And, hopefully this does not happen, but the baby's health could get impacted because of that. The mother's not being careful because she thinks she's not pregnant, or she's upset that she's not pregnant, or many other things are happening. So that's what I'm trying to say. So sometimes to realize the value of a true negative, of predicting you don't have the condition when you actually don't, we need to realize the harm of a false positive, of wrongly predicting you're pregnant when you're not. We need to figure that out. And to really appreciate a true positive, we need to realize the harm of a false negative, of wrongly predicting that you're not pregnant when you actually are. So that's why these comparisons, to appreciate a true negative, we compare it with a false positive. To appreciate a true positive, we compare it with a false negative. That's the idea. And so kind of bringing it back again, as we see in this part here, true positive A, false negative C, false positive B, and true negative D. What happens is, when we're going for treatment versus no treatment, if we actually do not have the disease and we're going for treatment, that's what a false positive is. We compare it with the fact that, hey, if I don't have a disease, I'm going for treatment, but like I want to compare it with the fact that I don't have a disease, but I don't have any treatment. That's what's happening. We're comparing these two together. This part here is the actual truth, whether you have the disease or not the disease or not the disease. But this is the, does a doctor predict you should go for treatment or not for treatment? So if we actually do not have the disease, we would be comparing going for no treatment, which is ideal. You don't want to be treated if you don't have a disease. But what would happen if we actually went for treatment, which is comparing B with D, as you were saying, and B with the D? This is the impact of a false positive relative to a true negative. That's what we can figure out. D minus B, B minus D. So basically, we're figuring out like why it's important for us to detect that someone who does not have the disease does not have the disease. And it's going to tell you somehow the harm of a false positive. And here, if we actually have the disease, if we unfortunately have this disease, then if we compare going for treatment, which is ideal, like a true positive, going for treatment, this part right here, with no treatment, then we can appreciate that I have the disease, but here I don't get treated. I'm a false negative. So if I'm being treated for the disease, if I'm A, I should realize that I may not have gotten treated for this. So what would have happened if it was a false negative? Like how many times we should be thankful sometimes, even if we have the condition, like thank goodness, that it was detected. Thank you. Because if it wasn't, doctors, nurses, staff says, thank goodness we could detect this on time. If it wasn't, then it could have advanced to XYZ stages. So good thing you came in when you did and we detected it when we could, so we can act on it. And then in the mind, you're thinking, what would have happened with a false negative? So that's the idea. So if we're comparing A with C, we're figuring out what is the impact of a false negative, compared to a true positive, but it's sort of telling us what would have been the impact of a false negative. Comparing to the worst case helps us appreciate what we have now and why it's so important that we correctly identify that we have a disease or condition when we do, because what would have happened if we did not do that and we did not get treatment on time. and correctly identifying that we do not have a condition when we do not have it. The true negative is important because what if instead we thought you had the condition but you did not have it? We give you a necessary treatment and you're a false positive. That's the idea I hope you understand here. So that's why, based on what we just discussed, I hope you can see that A minus C, the harm associated with the false negative result compared to a true positive, would really just be like, why is a false negative harmful? And that would give us appreciation for getting true positive predictions. And similarly, by looking at D minus B, we can look at the harm associated with false positive results compared to true negative results. So in some ways, D minus B is giving us consequences of a false positive and helping us realize why it's so important that we got a true negative if we did compared to a false positive. Like, what would have been the consequences of a false positive? Looking at the consequences of a false positive can give us more appreciation for true negatives. And looking at the consequences of false negatives can give us more appreciation for true positives. So I just hope that my little appreciation and you never realize what you have till it's too late, and kind of comparing yourselves or thinking of the worst case scenario, that's what we all tend to do, like in a way that this is sort of the intuition for decision curve analysis in a way. So I kind of want to talk again about this formula, but talking from Dr. Vicker's 2006 paper, the original paper that taught us about decision curve analysis. So basically, as we discussed, we have A, which is true positive, B, which is false positive, C, which is a false negative, and D, which is a true negative. So based on this, what this part talks about is equation 1, which is sort of what I've replicated here. This is equation 1 here from the paper, which is derived from the tree that we just saw. And what we see is that D minus B is the consequences of being treated unnecessarily, the consequence of a false positive, unnecessary treatment. If treatment is guided by a prediction model, which in our cases, let's say that we are using a prediction model, a machine learning model, outputs predicted probabilities, and then we use those if your predicted probability of having the disease is greater than or equal to the threshold, we predict you're positive, otherwise we predict you're negative. And please see my other videos for more background on that. So if we use a prediction model, then D minus B here, this D minus B is just the harm associated with a false positive result compared to a true negative result. That's what it means. It's essentially the consequences of a false positive, unnecessary treatment. Comparably, on the same vein, this A minus C that we're seeing here, this A minus C, it is the consequence of avoiding treatment when it would have been of benefit. That is the harm from a false negative result. So A minus C is the consequence of a false negative, avoiding necessary treatment. So you're predicting that the patient does not have the disease or the condition, but in reality the patient has it, so they are missing out on treatment that they would have needed. So it is the harm from a false negative result compared to a true positive result. So the false negative part is the C and the true positive is the A. So for the individuals who actually have the disease, we can truly predict that they are positive, or we can falsely predict that they are negative. And so this is the harm associated with a false negative result. That's what the numerator is, the consequence of a false negative. Whereas the denominator, on the other hand, D is a true negative, so those who are actually healthy, D. While B are false positives, so what we're looking at in the numerator is we're looking at A minus C, this is for diseased. So as Yang Shi is pointing out, this whole thing, the numerator, the thing that is on top. So if we have these two things, you have the top and the bottom, let's focus on the top. The top is, focusing on A minus C. So A and C here focus on individuals with the disease, actual positive. So they can be true positives or they could be false negatives. So they can be correctly predicted as being positive, or they can be falsely predicted as negative when they're actually positive. So these are the actual positive people here. Whereas D and B are for individuals who actually do not have the disease, the actual negatives. So D is the true negatives, those who don't have the disease, who we correctly predict are healthy, while B is the false positives. So those are individuals who actually don't have the disease, but we wrongly predicted that they do. So A and minus C, this first part is kind of focused on the people who have the disease here. So what are the consequences of a false negative of individuals who actually have the disease who are not kind of given the treatment that they need? Because we predicted they did not have it, we predicted they were false negatives. The mistake here is the false negative. And the mistake here is for individuals without the disease. The mistake we can make is false positive, falsely predict that they have the condition when they don't. So the denominator is concerned with the consequences of false positives, of unnecessary treatment. So if we're correct for the numerator, actual positive is true positive, otherwise it's a false negative error. Whereas for the denominator, the mistake would have been a false positive, because these individuals here in D and B, they don't have the disease. But in the case of like B, they may falsely be predicted as positive because they have a high predicted probability from the machine learning model. And these models, as Yankee believes, they're not perfect. Oh, he's just a little bit stressed. He's like, they're not perfect. They're not perfect. So they can make mistakes. So, they could make a false negative mistake. Maybe your predicted probability of having the disease based on the threshold and the model, it's you predicted as negative, but you actually have it, or false positive, where it's your predicted probability is either too high, or the threshold probability is too low. For whatever reason, you're predicted as positive, but you actually don't have it. So these are the harms here. So this equation 1, which is again, what we have here, it's talking about the threshold probability, and how this threshold probability, this PT here, how it can tell us, this probability threshold at which a patient will opt for treatment. If your predicted probability is greater than or equal to this threshold, we send you for treatment. This will tell you how a patient weighs the relative harms of false positive and false negative results. So in this formulation, harm is considered holistically as the overall effect of all negative consequences of a particular decision. So the harms, how do we weigh here? The harms. That's what we're concerned with. So just simplifying this down. So basically 1 minus the probability threshold divided by the probability threshold is just, A minus C is the consequences of a false negative, avoiding necessary treatment here. That again is, just the consequences of a false negative treatment, where, you have avoided necessary treatment. And the denominator is just, D minus B, which is the consequence of a false positive of unnecessary treatment. So that's what we simplified this down to, equals 1 minus PT over PT. So then the next thing that we do is we can just kind of simplify it out, consequence of a false negative times PT equals consequence of false positive times 1 minus PT. So it's something that is known as cross multiplication. So we're just essentially kind of multiplying. This side together. So that's, PT here multiplied by consequence of a false negative, which is what this is. And then on the other side, we have this right here. So it's all cross multiplication. Is the consequence of a false positive D minus B this part here is consequence of a false negative. Consequence of false negative, A minus C multiplied by PT equals consequence of false positive, which is D minus B, multiplied by 1 minus PT. So just rearranging them. And then next, what we're going to do is we're just going to isolate PT. So PT is just equal to consequence of false positive or over consequence of false negative multiplied by 1 minus PT. So you can kind of already see how this kind of, relates. So that the threshold probability at which a patient will opt for treatment, this PT, is informative of how a patient weighs the relative harms of a false positive and false negative results. So this part over here, we're seeing here, how a patient weighs the relative harms of false positive and false negative results. That's what this part kind of shows us over here. Note that the threshold probability is on this side here, but if you think of it as just kind of showing how view the consequences of a false positive over the consequences of a false negative, a false positive to false negative ratio. And then what we'll do is we'll just I just wanted us to flip this around, because in the decision curve analysis formula, it's PT over 1 minus PT. So that means we're just going to divide both sides by 1 minus PT. And then we're going to get the final result, PT over 1 minus PT, which is equal to the consequence of a false positive divided by the consequence of a false negative. Therefore, the probability threshold over 1 minus this probability threshold is the ratio of the relative harms of false positives to false negatives. And these relative harms, they're considering everything, like how you weigh everything. So for the false positives, going for unnecessary treatment is one. Then also, paying for unnecessary treatment, the stress, the side effects, the heartache, all of that stuff that you're going through, the stress, all of those things. And maybe the side effects could be pretty bad, from a false positive. Financial concerns, lot of life, energy, time spent, unnecessary chemotherapy, for instance. Maybe that triggers a cascade of other results, as well. It's financially expensive, a lot of stress that you've been through. And for false negative, it could be that maybe if we had detected the cancer earlier or something like that, it could have been prevented, and now it has progressed to a very late stage. And maybe if it gets cured, there'll be some lifelong effects that you're going through as well. So there are a lot of different things there that we need to be concerned about. So thus the probability threshold over 1 minus probability threshold shows how we weigh false positives to false negatives. And in fact, this is a key part of decision curve analysis. And I talk about this a lot more in other videos here, but this is like the whole overarching idea, as Yankee saying, of decision curve analysis. It's the whole overarching idea of decision curve analysis. We have a probability threshold. If you're positive, if you're predicted as having the disease or condition in this case, that's usually what it represents. If your predicted probability of having the condition is greater than or equal to the threshold. Otherwise, we predict you're negative. And then the decision curve analysis calculates clinical net benefit. This formula is for the treated individuals, those who are predicted as being positive. But it's the same, and I show in other videos, it can be the same for net benefit on the untreated or net benefit overall, but this is net benefit on the treated. True positive count over n number of individuals in the data set minus false positive count over n multiplied by the same fraction that we saw, PT over 1 minus PT, and now as we just saw, this ratio here gives us the relative weights of, the harms of false positives over false negatives. That's what it does. So it helps us interpret the relative importance of both types of mistakes that are possible. False positives, falsely predicting that a healthy patient does not, a healthy patient who actually does not have the disease, falsely predicting that they have the disease, versus a false negative. So where you falsely predict that a patient who actually is diseased has the condition, you're predicting instead that they are healthy. So how do you weigh them? That's what this ratio tells you. So we have other videos on decision curve analysis, so please do subscribe. I just wanted to motivate sort of how this probability threshold represents, relative harms of false positives to false negatives, which is something I talk about when I explain, like, probability threshold of 25%, for instance. What does that mean? And various other probability thresholds, how this is kind of like a currency. So again, how a patient weighs the relative harms of false positive and false negative results. That's what the threshold probability tells us. So I really hope that you found this was helpful for you now to wrap your mind around why the probability threshold over 1 minus probability threshold is a way for us to inherently weigh the harms of false positives and false negatives. It's like a currency. So we can sort of show how we prefer the mistakes of false positives to the mistakes of false negatives. How do we weigh? How do we weigh those results of falsely predicting that a healthy patient has a disease, unnecessary treatment, with false negative, wrongly predicting that a diseased patient is healthy and they are avoiding necessary treatment in essence? How do we weigh that? And that's what this probability threshold, this formula here, this ratio is building in. Our preferences for false positives and false negatives, all with just a number. We give a threshold and it computes in a way that the way that we weigh these. And I'll talk about this in other videos, how this threshold shows the weights for false positives and false negatives. But now you can kind of see that when we're calculating clinical net benefit here on the treated, we are inherently weighing the false positive with false negative errors in and of itself through this. This part right here is fitting in right here. And in this formula then, it's more like true positive count over n minus false positive count over n, and then weighing it by false positives over false negatives, and we are getting this kind of inherent weighting from this probability threshold. In a way, that's what it's representing, and that's why decision curve analysis is often a superior way to do clinical decision making and model evaluation. So I hope that you found this helpful. So please reach out with any and all questions, but we will be building out on this in our decision curve analysis playlist here. And I give a lot more explanations on decision curve analysis and this formula. So please do check it out. Please do subscribe. Please see my other videos on probability thresholds as well. So I hope that this is helpful. I'm Saniya, and this cute little sleepy guy is cute little Yangshi, and he's gonna give you guys a huge hug. Bye guys.